Everyone. Yeah. So the format will be that
Hello.
we have, of course, our four panelists. You all know them past week. The format will be the panelists have already given some issues that they are thinking about, and we will. Each panelist will pick one of their issues which they think is most important to discuss right now. Speak 1 or 2 minutes about it, and then 3 minutes we have a first round of reactions, one minute each from the other panelists, and then 5 minutes open conversation. So that goes on for 4 such topics, and then the audience chooses 2 of the topics that they want to discuss on the issues which I will just show you, and after that we have some open questions. Sounds good? Yeah. Okay, so these are the topics. Right now we could even go in, it's quite dense, but at least the one who wrote it will know which one is most important. So
It would have been better to
sit there. We can still pull things a bit closer.
It's fine.
You remember, yeah. Okay. So shall we just maybe go in sequence? Sequence of this?
So yeah, you
Yes.
decide.
Shall I decide? Maybe let's just go in the order in which we are sitting.
Sometimes having less options is better.
Yeah, so okay, so order. So maybe Maryam, you can start with maybe with the microphone is needed. Shall we maybe pass this mic around? This is more convenient than I feel. Yeah.
Oh, it's muted. Okay. I wrote my problems, but I'm trying to decide which one is the first one to go. Okay, maybe I start with the first one. So the one question on my mind is theory practice gap and how what are some approaches that we can close this gap, and or do we want to even like, because sometimes I see that the theoreticians work on just a theory and it's nice and beautiful, and then the practitioners also make things work and it seems to be working, so why do we need to so if it's working, so why do we want to close this gap, and if we want to close it, how can we close this gap? So these are some things that are in my mind. So how does this work? I leave it for the panel to discuss.
And then the panel
Okay.
reacts.
Okay.
Then we discuss. Yeah.
There are two issues here. I mean, one is explaining why things are working when, practitioners are hacking away. And the other is how can we convince our students to learn about Markov chains when they could just wake up and play with, get ChatGPT to write code for them. So, and I have the same question. So I have no answers.
I think that we see lots of shiny results, but at the same time, only the successes are selected, right? So what people see is a super biased sample, and it has led to, I think a crisis in machine learning, right? Nobody knows whether yeah, you pick up a paper and you expect it to be true, but you implement it yourself, and what are the chances that it will work for your problem? Very low. And so I think many people will easily recognize that there is a problem and that getting theory is important to fix it. But yeah, indeed, I think so. It relates probably to the third bullet you have there as well. Things are moving so fast.
Yeah.
So then how do we really get people to work on which one of these problems, right?
Yeah, so this is, I guess, because also with applications, now GANs are hot, and then the next day is LLMs, and then I see students going from this to that, and theory takes years to maybe establish something. And so I find it a bit of a hard landscape I'm trying to navigate, at least. Yeah.
But I will say an action item is to get NeurIPS to force authors to report failures. It really should be, just
Yeah. So
I think
I agree with it completely, and I think reporting failures are a very important part of science, and which we often omit because probably of the publication business you have around it, right? So it would have been very nice to know for students, I think, to what not to try, because often when I go for like very practical projects, I find like at least 80% of the time we try things that don't work. And then finally 20%, after all this elimination, you understand what works roughly, what is the sweet spot, and you go for that and just publish that. But think like another student starting that same project, wasting 80% of time doing the same thing is a pity, right? Is a pity of loss of time, resource, everything. So I think it would be very nice to publish negative results. That is one thing, what does not work. And the theory to practice gap is also very central to what I try to do typically, or what the problems I try to work on. So like if you see the questions, I think they always about like what are the minimal assumptions we need to really build up a theory that works in practice, because in practice, most of the cases, as Son said, like you wake up in the morning, you take your favorite package on the favorite environment, and it works. And why would you, go through all this painstaking theory? The question is, can we make a theory with minimal assumptions? That would be something very nice. So, yeah.
Any other comments from others on this topic? And yeah, from you. Yeah.
So if you mentioned, show, like completely agree with it. Currently, having those negative results, using your statistics would increase it by further 8%. Well, like 100%. How would you then figure out how to navigate the, or to all of it, if people start publishing, how, in general, how do you navigate positive results, and then in the case of negative results, just even worse, right?
Yeah, I think that's in general a problem that we have plethora of papers, basically. The number of papers is more than what one can ever digest in, even in very specialized topics, basically. And often you find like if you try to publish so much or like read so much, the differences are often very epsilon. So yeah, it's a crisis in general as a ecosystem we have, but I don't know how to address that. But negative results are very interesting, and in between in Europe there used to be a workshop. I cannot believe it's not better, and there they are accepting lots of nice ideas which you think are theoretically very nice, but probably didn't work in experiments, or vice versa. And that workshop, actually, when I attended at least twice that workshop, it was very nice. You see lots of interesting things happening, but somehow they don't work, no one knows, but you still communicate, try to have a scientific discussion. So some forum like that, maybe an open review of negative results, I don't know, that can be helpful.
That's not what I had in mind. I mean, imagine if you have a numerical experiment, it's an expectation you do something to show some parametric robustness, maybe, or something. You leave it up to the author, but not just take the ideal setting, run it, and say, "Hey, look, it worked," and walk away. So leave it up to the author, but I mean, or an estimate of how often it worked. I mean, yeah.
I have perhaps a bit of a different perspective. Yeah, I think it should work. And well, I mean, if people can't hear me, then let me know. But so I think on the one hand, yeah, I mean, there's too many papers already as is. So actually, it also doesn't matter, right? Like, I mean, I will read some number of papers, and then the number of papers that I don't read personally does not really matter to me. And I mean, this is what ChatGPT perhaps is good for,
Yeah.
right? Like, I mean, ChatGPT, or I mean, this is technology that sort of works, or at least we think. We don't know how unbiased ChatGPT is in coughing up now particular results, etc. But in principle, there's technology that can summarize a lot of this stuff. And we will get better access, therefore, to knowledge, the knowledge that we're, trying to find. And so then just having those negative results out there, I think it's only good. I think that's one aspect. I think the other aspect is also because, currently we also have a lot of papers that are being published because we select on, these empirical evaluations. Now, the paper got in because it was 5% better than the previous state of the art or something. But then the IDs that are behind those papers are quite often, I mean, there are many good papers, right? But there's also quite a lot of papers where it's really not clear what the new idea is, or there's some idea, but then in order to actually get it to work, there were these giant other number of hacks that were also being, thrown into the paper, because apparently the idea by itself, didn't work. So right now we have this kind of like situation where nobody really assesses IDs and everybody only assesses numbers. And perhaps, that also leads actually to having many more papers, which perhaps not all of them are really as relevant, right? So I think we should really move to a setting where we try to assess IDs. And then if they work or not, well, that's just the experiment that follows, right? So yeah, and so I don't know precisely which field, but apparently in some fields or some people were talking about this, where you would go to a way of publishing, which is a little bit more like grant writing, where you would propose like, okay, well, I have this idea, this particular hypothesis, of something that could work in this type of problem with this whatever type of structure. And you submit this together with somehow the experiment that you propose that you will execute, and this would be reviewed, right? Somehow, and so if it's an interesting idea, somehow, yeah, people would say, oh, great, interesting idea. You can publish a paper about it, including the results that you're going to generate. Right, and so if we would move to something like that, I'm not saying, I'm certain that it's all kinds of ifs and buts and whatnot, but then we would move to a setting where we're assessing somehow the ideas and the novelties, and would it be interesting to know if this works without assessing whether it actually worked, yes or no. And yeah, perhaps that is a way of taking away actually the incentive of just publishing, many more papers with some delta increments, but without any actual IDs.
Good. Let's move on to the next topic.
Yeah.
Okay, one last and then, because it's already 15 on this topic.
Do you think about this advanced simulation tools like IDEXing or anything like a hardware input system? Do you think that these systems or tools are good enough to solve this problem?
I think they maybe solve sim to real, but they don't solve the theory to practice, like because they still whatever we implement in Isaac G maybe still too complex for our theoretical analysis, because usually, at least from my little experience in that and understanding is that it's more on sim to real. But the algorithms there are still not the ones that we analyze. They're already too complex. Does that help?
Okay, thanks. So we move on to one issue from Deb.
Yeah, so I think 4 of my first issues are different type of theory to practice gap questions, I think. But since it is control plus RL, maybe this would be an interesting question. The last one, that typically when we try to do RL for control, we go up to LQR and stop, right? So like anything except LQR that you think is interesting or doable from an RL perspective, and if there's any other model or any other setup that you think is interesting to study as a control, if you put up the control hat, like what would it be?
You can hear reactions from others. Who would like to go first?
Yeah, I think, I mean, I can.
Yes.
I think in control we love our LQR settings, and because it's we can understand and we know what the solution looks like, and also it helps address many systems in practice as well. But I think in terms of the RL, it's more like it helps us to know what is not possible, because if we cannot solve it for LQR, if this method doesn't work, then it tells us in other continuous, it's more more like a check, like a more complex, like not continuous state and actions. If it doesn't work for LQR, it probably won't work for those either. So I think that's, for me, that's one of the main insights it can give. But as you said, we shouldn't stop there. Now, what else we can look for? I think in control, we also, at least in this optimization-based approach to control, we look a lot at convex, some problem structure. LQR is linearity because that literature was developed in the 80s, and now then it came convexity in the 90s, and then we have a lot of, in control, we do a lot of convex methods like semi-definite programs or model predictive approach. And that what structure does that give us in terms of proofs? So I think it's more about problem structure that we can maybe leverage. And I think in RL, people are also starting theory. They're starting to do that with function approximators. Yeah, I don't know. I have.
Frans or Sean?
Yeah, so I guess I'm not completely certain what the question or so I understand this a little bit as, you know, is there some set of prototypical problems or benchmarks that we should really somehow care about? Is that
Yes.
what you intend?
Yeah. Yes.
And I think that's a good question, and I don't have the answer per se, right? People often think of artificial intelligence as a bunch of techniques that do cool things, and to some extent, I suppose that's true. But I like to think of artificial intelligence also as actually trying to understand the world around us, right? It's kind of like understanding what computational methods work well for problems around us in a way, right? And what the structure of those problems around us have, we don't really know in advance. It's really by, trying to explore these computational methods that we better understand their properties and structure. So I suppose I would argue that it might be good to have, or try and think of some set of problems or domains with particular properties that we already know that we care about, but that it's always very important to try and think of new types of structure or different types of problems. And we have no idea whether they could be relevant or not, but who knows? And we might learn something about that world and how we can computationally interact with it.
Yeah, there's a risk. I'm just, the old man here. Yeah, in the early 90s, all the funding for control was coming from the military. And when that dried up, well, everyone was told, go off and find some applications. And control community completely was fractured. So there's some people doing chemical engineering. Nobody went to the chemical engineering talks at CDC, the control conference. So there's a little bubble of people there, a little bubble of people doing, semiconductor manufacturing, whatever, scheduling. It completely fragmented the control community. So there's a balance there. But I should say about LQR, in a way, I push back on the fact that it's a good example. It's good because we know the solution, but it's bad because it fails for like Q-learning for this very special reason that you get a non-Lipschitz right-hand side in the parameter. So it's such a artifact of the structure that it doesn't generalize really. It's just one warning: be careful about Lipschitz continuity. Rule number one, right? But anyway.
Yep. Thank you.
Thank you. Any more questions on this from the audience? Or okay.
Your own personal experience, how important was the sort of interdisciplinary contact with other fields? For instance, some RL algorithms are inspired by biological processes in the brain, or maybe some idea from completely different field affected your work. Are there any sort of your personal experiences where you were inspired by something completely unusual? Or like maybe not even scientific or by just some observation during the day that was inspired you to do something?
Maybe on you want to start? We can go.
I mean, I could say that like spending time looking at queuing networks got me excited about trying to find structure, and that led me as a goal to find, to use that structure for architectures and queue learning. It sort of failed up till now in specifically that domain, but I've used it in other domains. It's like finding it really can be valuable to find some structure for value functions or policies, and then use that for architecture. So that's, but mainly it's very exciting to make connections with other researchers of other fields and learn from each other. So it's just, I mean, it's the best kind of research. Yeah.
So I think for me, I could also add perhaps a little bit, but I think trying to get a broader view of things and understanding and seeing commonalities, I think is very important. And then, yeah, what constitutes a different field? Like, this is often a difficult question, right? I've tried to somehow, do some work on bridging, perspective from POM de piece to game theory and game theoretical views. Yeah, that all can be somehow viewed as perhaps within AI, although game theory community also is already a little bit separate. So it's not like I have personal experience getting indeed, I don't know, insights from biology directly, right? But somehow, working towards understanding how things are similar and trying to get unified perspectives, I have always found it very satisfying personally. And I also think it's very good because it then brings actual understanding. And also there, I think there's tendencies currently, particularly in publishing, to try and write stories to make things seem as dissimilar as possible to previous methods, right? Or not even mention them. Oh, this is so new, nobody ever thought about this. And I think if you read something like that, you should be extremely critical because the chances that something is really like completely novel, they're rather slim, say. So understanding how things relate is very important.
Okay.
Okay,
So maybe I can go ahead. So for this, actually there are general answers that interdisciplinarity is good. Often like you can take motivations from each other, but though how much we do in reality, that's the question. I can give you two personal examples where it has been very helpful recently. One is in the project that we are working with Aditya, we had a postdoc, we are trying to look into how to put causality with RL, right? And we found out a lot before computer scientists, really economists thought about that. And they really thought about how different policies, interventions cause different changes, different outcomes, and they have developed a bunch of techniques for it. And when we tried to do, tried to import those techniques to bandits, to RL, to the theory, to the statistical analysis, we found there are lots of open caveats, lots of challenges, but the technique finally that survived, the algorithm that survived comes really from economics, which they call instrumental variable regression, two-stage least square, etc. And then we brought all our statistical knowledge to do a very banditish analysis of that and developed a bandit. But it is really the econometrics people who did decades-long work to make the algorithm and make the idea. That was one case, and the another case where I'm learning a lot is again another project with Aditya and Guillaume, where they are trying to design this kind of bioplausible way of learning a time series. Okay, so basically you don't have luxury to take a back propagation anymore. You always have to do everything through a forward pass. So something like a physical system that wants to learn something, how you can move the physical system from an initial state to the learned state, basically. So that's, again, I'm learning a lot, so they know much more. But I find it fun sometimes, not to do things that I know, completely start from blank and learn. Then it becomes a bit more exciting.
should we move to the next one, or
Sure.
do you want to say something on interdisciplinarity?
Maybe just briefly, and I guess, I was reflecting, I'm always inspired from other or applications. I think I always get inspired, but maybe just something a little bit that wasn't the only thing I would add is I also find that it's really important. I mean, it's good to be open, but it's also so important, at least to my students, I say, is to first go very deep in something before. I mean, you want to be inspired by all these ideas, but you have to first also go deep and get the fundamentals. Then you can open up things and connect things. So that is something I would just add.
Yeah, it's always a trade-off
Yes.
between depth and breadth. Yes, now may I request Frans to pick an issue?
Yes,
from
you
the-
may certainly request. Let me look what did I write down again? Yeah, there's no such thing as optimal exploration.
This was a reaction.
Yeah,
to
that was a
Bert.
reaction to Bert, who had the statement. There's no such thing as optimal exploration, huh?
Yeah.
And so, well, I don't know. Perhaps it's interesting to reflect on this a little bit, at
Yeah.
least, given that there is at least a possible difference of opinion about this. I think so. Of course, I can't look into Bert's mind as what he precisely would have meant with his statement. There's no such thing as optimal exploration. I suppose we have many no free lunch theorems, and somehow we think of exploration as a type of search, and then there might be not a optimal search strategy because well, it all depends on the actual structure of your problem, and for every problem where going left could be optimal, there's another problem where going right would have been the best thing to do. But at the same time, I like somehow being Bayesian or pretending to be a Bayesian. And if we have prior beliefs, then we can define things like optimal exploration, right? So there's these frameworks like Bayes adaptive MDPs. Shimon Weizen gave a brilliant talk on this at some point at I think NeurIPS workshop. I don't remember, where he also had the exploding brain thing, right? But yeah, it's really kind of cool, right? So you can just somehow write down in math, in uncertainty, you have a probability distribution over, what is the transition function say of your MDP that you're uncertain about, but you have a belief about this, and that belief, we assume perhaps we know the reward, we know what the states are, etc. This prior belief now actually implicitly induces a optimal strategy that optimally balances exploration and exploitation. So yeah, I think there is perhaps such a thing. Then whether it's really useful, I don't know. So that's something perhaps that we could debate.
Again, I'm not sure how to add to that, whether it's useful or not. We could come up with wonderful mathematical puzzles, which is really 50% what we're after anyway. So I'm all for that. Yeah.
No, I think that's a very interesting question by itself. Like when Bert said, like, I think he had a very different thing in mind, but the bandit thing is really nice. Like once I got the opportunity to work on that, and it was very interesting. But yeah, the practicality, yeah, applying that even on like a big grid world was a tough thing, basically. Like really applying the MDP algorithm. But yeah, probably there's a theory which should be explored at some point. Yeah. But really, like, I wanted to know what Bert meant by like, there's no optimal exploration. Maybe there's a different definition.
Yeah. But also in this issue, what is optimality? Like, what are we optimizing and what should we? Yeah, that is also a big question, no? Like, people then go towards multi-objective and so on, but still, like, how do you even define objective and what should be optimized? And
So I would argue then, that should all be captured by your belief, your prior belief, right? You can be optimal with respect to your prior beliefs, I guess is the argument that I'm bringing. Whether those prior beliefs are sensible or useful or where did you even get them, that may be a different story. But in principle, if you're able to mathematically specify your beliefs about a sequential decision-making problem, you can turn that problem into essentially a planning problem, right? So you take a learning problem, you recast it as a planning problem. You're planning in the space of possible beliefs you could have. If I do this and if I would observe that, what would my belief then be? Right, and you somehow do the planning in that space.
Yeah, so this problem also is pretty interesting because at some point, like as a bit infatuated with the geometry of this problem, you know, how in the belief space you have an optimal path, like the least path in there. That was very fun to do, but again, yeah, scalability becomes the issue, and the specification of belief in reality, like that's very hard. If you have a discrete set of arms and state, and you know, observe everything works well, you have something, but more than that, how to do it, maybe that's also an interesting question to think, reflect on.
Anybody from the audience? Yes.
The topic of optimal exploration, I know that there were some work, like they working on drug control, right? That basically was trying to solve exploration of problem optimally. Did you ever draw inspiration from their, in a certain sense, negative result to wonder about how to less heuristically do exploration or find maybe some computational efficient methods to solve that original problem? For example, like parameterization, something to solve.
So I personally only relatively recent found out about this whole dual control literature. I was really exposed to this idea via the AI community, the base adaptive MDPs. Indeed, it goes back to the 60s or something, I believe, where some people already tried to look at some of these problems. I'm not completely certain about the negative results you really refer to now. Can you explain? Is there a
more
particular?
like the first opinion they found out that it's solving the problem was really the hard problem.
Yeah. Yeah, sure. Yeah, I mean, solving an MVP also is very difficult in practice, right? Like, so yeah, I don't know. I never feel held back by scalability concerns. I feel held back by reviewers who point out scalability concerns. Just give me the money. But no, yeah, no. So yeah, I think. It's a very elegant way of thinking about the problem, and indeed, there's perhaps lots of progress that we can still make in that area. That's how I see it.
Yeah, but scalability, I think, has always been an issue in RL. You know, now people come up and say like RL is used for PPO. I remember in my first class, the second class, the professor said, okay, this is a very nice thing, but due to curse of dimensionality, probably we never apply it anywhere in any time soon. And like in 10 years, we have seen like everything getting changed, right? So, and that was rather for me is the thing that made me interested in RL. Like it's a hard problem. Let's, you know, work on it. Let's have fun. So I think scalability is not a bottleneck. It's more problems for you to work in future.
Great. Yes. Oh, maybe there's one more question.
If you have a fast reward setting and the rewards are not, it's not possible to guide exploration to reward. How can we guide exploration? Like how do we guide the agent to move towards the goal and not just do some random actions in the environment?
So you're asking in specific about exploration with multiple agents in a multi-agent type of setting. Yeah, so I think there have been certainly a couple of papers that try to explore some of these things. I'm thinking, in around 2007 to 2010, Victor Lesser had one or two students that were trying to explore some of this work where, you know, they would have agents that would coordinate in some way or form some hierarchy to decide when they would take exploratory actions and when not. So I think somehow revisiting some of those ideas could actually be quite interesting. And yeah, you know, nowadays you can try and couple this with models that you try and learn of the environment, right? So yeah, I think it's certainly not a trivial problem, but I do think we have lots of tools to try and tackle it.
I-
Oh, yeah,
But actually, in response, I mean, I think that, I mean, you know, obviously, we could all write a paper on control without sensors. If you're completely blind, there's not much you can do. But obviously, but the thing is, in RL, often people really don't take advantage of the fact that they really did see the gold mine, and they should really, you know, make really good use of the fact that they saw the goal once. And I think that we blindly code sometimes and don't use exploitation properly. I think that's the issue. Sparser words, I don't think is so detrimental if you design the algorithm properly. That's a conjecture. I mean, I can't prove that, but yeah, um, that's all.
Yeah, then maybe we ask Sean to pick an issue. So, and
You know, so I didn't prepare at all really. So Aditya asked me to come up with some open questions, and I just blurted out some jokes in a way. I mean, because all these are just too vacuous in a way. But about shackles of Bellman equations, we're not going to get a supercomputer like our brains with Bellman equations. I think we need a different paradigm. But the first one, I really think could be exciting. I mean, someday somebody's going to figure out why Q-learning works. You come up with some crappy basis, you run the algorithm, and you get a good policy, even though there's no reason why that should be the case. I just think that's a wonderful open problem. There's some way to look at Q-learning, and we'll figure out in the next 10 years, why we often get really good policies. I mean, even with just the silliest architectures, yeah, like for multi-agent control, you just cook up a Q function, so it would give rise to a distributed control solution. You run it, and poof, you get a good solution. The cover of my book is an example of that. It's a randomized policy based on a stupid hack. So I don't know if there's much to discuss, but it's a fun, open problem. It's in non-ideal cases, why does it work so well?
yes. Okay.
Mhm. Oh, right, there's all this stuff, but yeah. Well, I mean, you can go and listen to video lectures by John Doyle from Caltech over and over again about this. He loves to talk about fragility and robustness, and he became famous because Rudy Kalman was the god of control, and then John Doyle gave us examples showing you got the optimal solution, but it was just worthless because of sensitivity. And that helped to launch the field of robust control. It was already launched, but that helped it was sort of good advertising. And so that is a problem with the RL community. There's a complete singular focus on optimality when the control community realized in the 80s that that's a mistake. So how we can soften our objectives to take into account that first of all, we don't, except for advertisement, where you just want to make as much money as possible and you don't care about anything else, take your bonus and go and retire. In almost any of our application, there's, robustness is more important than anything. I mean, you think about autonomous driving, can you imagine that a single objective you like to optimize? It's absurd. And once you realize that, that we have such a gigantic playground to play in, just reformulating the problem. It should be liberating, it should give us all sorts of new control solutions and methods for learning. But I don't have an answer to that. It's true, because it's too general. That's the other thing that the control community learned. Nobody expects to come up with a a super duper RL algorithm that's going to solve air traffic control and you know, insulin control at the same time. You know, you have to, you know, develop methods for particular contexts. I think that that's well understood in the control community. So,
Yes.
which is it's a challenge for us. I mean, again, because we want a community, and you know, as soon as everyone specializes, the community is destroyed. So it's a really tough balance.
Maybe Maryam, you on the thing of optimization, because you work on this constrained optimization, which to my mind at least might bring in things like, you know, other things like safety or robustness and so on. Could ultimately that's also optimization. You just reframe the problem, the constraints and the robustness into back into optimization. So in the end, is everything optimization as long as you get the
You build the right objective.
exactly. What are your thoughts? You agree or disagree? Or?
Yeah, I mean, at the end, whatever we do, we encode it mathematically in some objective, so we can incorporate robustness or safety, but yeah, that's how do we, I guess the RL doesn't do that so much yet. It focuses just on the optimizing a given objective and usually a discounted sum objective. And it puts everything, I think, in this objective, from the constraints and penalty for this and constraint for this, everything is mapped in that objective, and that's not maybe representative enough of everything we want to do. I mean, there's now some works that they try to do distributionally robust or min max, but they're very theoretical, and I don't know if and I think the challenge also is they might become way too conservative. So to find the right balance to incorporate robustness but not become very conservative. That's a challenge, at least in autonomous car applications. We found that when we make it too robust, even with our robust control method, the car will not move. It just doesn't find a solution, right? So I think that's also a challenge. How do you, as a human, we're not like too conservative, we find a way to move forward. But when you encode that mathematically and think about all the things that uncertainty could do based on the sample of the distribution, you try to be robust to more things, and then you might not move. So how do you incorporate these things? Yeah, I think it's open, interesting.
Frans, you want to say?
Yeah. So I'm not certain if the question was really specific to reinforcement learning, actually. But in reinforcement learning, it is certainly the case that, so the way that we typically set up what is the objective is how much do we expect when executing this policy, right? And then that means that we're evaluating the reward on the trajectory as generalized by that policy itself. And so actually, Miguel Sau, my former PhD student, he came up with this sort of idea that, yeah, there's perhaps this kind of like overfitting to, well, those trajectories. And so you need to have this kind of like robustness to out of trajectory generalization, right? Like, so somehow in game theory, there's a sort of similar kind of notion, right? There's this a notion of, let's say, trembling hand equilibrium, right? So you can somehow say, well, these policies are in equilibrium, but then what happens if somebody makes a mistake, right? And you end up in a different place, a somewhat broader set of trajectories, if you will, right? And so perhaps indeed a thing that we might want to consider in RL is have, well, sort of, well, on the one hand, what we want to optimize, the policy and the behavior, but also somehow specify perhaps the distribution over trajectories on which you would want to achieve that good behavior, right? And that could then include trajectories or positions that you would not expect to end up in, right? And it's indeed kind of important because also, somehow Miguel's reasoning was kind of like, well, so we're training an RL agent, and in the beginning it's, you know, all over the place in our entire space or entire grid or entire whatnot, and it learns to take good actions in all those places because it can end up in all those places. But then once you go further and further and train more and more and more, and you get more and more and more optimal, also you're seeing less diverse and less diverse and less diverse data, right? So. Yeah, so yeah, via the RL itself, you're narrowing down your training distribution such that at some point you're not robust anymore outside of it. And perhaps this is actually why Q learning is sometimes good, because you can somehow be much more broader in the the trajectory distribution that you throw in, because it's off policy.
Interesting. Yeah. Yeah, interesting.
No, I think that was a very, very good question, actually. And this is also very ambiguous, as you see from all our opinions, that what would be the new objective, because optimality is something that we were taught, we overfitted on that as a community, for a long, long time. Now we understand, like, we want something more, like we want generalizability, like generalization, bounds. We want, like, so maybe generalization in the sense of the trajectories I see in reality. They're not that extreme, like, so I have probably a distribution over what I can see in real life. Maybe I work on that. I try to generalize over that. That can be one way. The other way can be like generalization over tasks. Maybe some algorithms are good to generalize and transfer things over tasks, basically. So how can I learn models of the world, or like can I learn some kind of parametric way in RL, like policies, parametric policies that can generalize over tasks rather than just being optimal for the task. Because most of the things, like if you think of humans, we are not probably the optimal solution to anything in the world, but we are a very good workable solution to most of the things in the world. So yeah, so I think that's something that should change, and that also comes from the point of reproducibility. Basically, if you really see what happens in the real world, if you really want to have an algorithm that can reproduce across such trajectories, observations, or tasks, you should have a more reproducible algorithm. That should be another objective or another way of looking into robustness. Like in distributional robustness also, they try to be good across distributions, like a set of foundations. So people try to encode it in different way, but I think this is very ambiguous to be encoded in one method. So yeah, probably we have meant to.
Right. So now we'll open you can pick, okay. So just before, you can pick one from here and then the person could expand on that. Or if you have your own, you could ask now. Does somebody, okay, maybe, yeah. Go ahead.
So I see like as a gas or lecture on why the learning works, because even from the actor credit, the learning actually use random exploration and greedy. Maybe because it's greedy and random exploration will work, because actor credit, they change the actor is kind of what is greedy represent the replacement of the greedy and random exploration, and credit is kind of similar to that.
Well, actually, though, there's such a firm, beautiful theory.
Yes,
You learning, because we're in my lecture, I mean, that projective demonstration is such a joke. I mean, I don't know how to interpret it at all. Outside of the kind of case, actually causing a problem. You know what I mean? It's just specifically to learn. I think that it is.
I think no problem right now. We already do that. So maybe a lot of problems.
Well, that's a good question. But I think, like, I'm embarrassed about that up there. PPO, what I mean by this, exactly, before is that it's perfect theory, everything's exactly right. The way people implement it, it's so real theory, and it works anyway. Yeah, that's a very similar question. The robustness, apparently, my experience, the robustness of the algorithm is wild, and so, ideal cases like active critic, when I know I should suggest it with that, in the left circumstance, people throw away all the theory, and it still works. And clearly, where I have no theory at all, I run it, it works. And I want to know why.
As long as you do gradient clipping, right?
No, the day of that business, right? So I've never even tried. But the Q learning with no theory, I find it awful. And I don't know why. What's it? And they're very take a long time to run. Yeah, I don't know. We continue. That's about
Question there.
They try as an example for Q active learning, not floating.
I don't understand the double triad. We were discussing that. I just don't understand it. You know, I really don't. I mean, yeah. What are the three again? Do you remember the three?
Yeah, but
Function, go ahead.
combination of, approximation,
Bootstrap.
bootstrapping, which is like long way to zero.
I guess. I don't know. Yeah, yeah. It seems to me, I don't know. I feel it's a lot of issues. I mean, I don't, to me, it's accurate. I mean, you know, I mean, the three properties, I don't see how they really address the question. Is that we're trying to solve the projective dominant equation, and it doesn't mean anything outside of the box. It doesn't mean anything outside of that. And boiling that down to three things, like every triad, I don't know. I see a single, monopod, the projective dominant equation. You know what I mean? Outside of that. But the fact that it works means there must be a reason. There must be some way to really interpret the equation. And it might really help it once you understand it, but then it really is to help the basic question, things like that. But if anybody understands the really triad, again, that's another topic we was. I really understand. I'm not afraid of it. I'm not crazy.
You mentioned properties, you never properties.
Well, no, it's just that, I don't know, one of them is just the property of a particular algorithm, but that's what you maximize in. That's just the property of the algorithm. I looked at that, I don't know. The function approximation is real, absolutely. But the fact that we often have very terrible bases in situations anyway. But that's to me the thing that's just fascinating.
I think one of the dangers of thinking about deadly triads is that we presume that we're safe as long as one of those things is not satisfied, right? Which, yeah, I don't think is particularly true. I think, well, so I view deep reinforcement learning now as, no, it's not really a technology, right? It's more like an art, right? Somehow you get some people to, spend some time and tweak, and so people are exceptionally good at getting these kind of things to still work, despite that they don't really work, but sufficiently good that you can do all kinds of cool stuff with it now. But yeah, somehow understanding and taking away the magic and being able to, of course, automate this and deploy it reliably, that will be a game changer.
Yeah, so I think everything I almost wanted to say is said, and also in the lecture, like what I said, though people say there's problem, there are some counter examples that people try to work on, but in reality, you rarely see it. You like if you do experiments, even there are experimental papers after deadly triads that really show that okay, diverge initially a bit because you have very low sample, very big networks, nothing is trained at all, and after that you actually don't see much happening. Maybe high variance, that's a problem we know coming due to different reasons. So it's not very clear. Either like we don't understand the science of it, or it is something very specific degenerative that happens in very specific MDPs or whatever. Yeah, so I think more than that, I don't also have an understanding.
Okay, next question.
Discuss some more what do you mean by active learning of causal world knowledge?
Yeah. So I think, well, so we were kind of asked for kind of like open problems. Huh? So what did I wrote down? Oh yeah, active learning of causal world models. Yeah, so this is essentially what I am very interested in. So I think model-based reinforcement learning is really cool because I really think that it's nice to somehow learn to understand the world, and then if you have such a model, and then you can plan with it. I mean, this is essentially what people have always anticipated, right? Like when the MDP was invented, this was the goal. Somehow you try and model the problem, and then you plan with it. And so I think that's a very sensible way of trying to deal with problems. And then if something changes in the world, you quickly adapt your model and you can replan and somehow have a new solution. The problem, of course, is that a lot of the deep models that currently we're learning, there's some latent space and we really don't understand this, and this can be highly non-structured if you don't put in some additional constraints, etc. It's really, you try and plot it, it's one crazy, mess of points that are somehow, being compressed in some latent space, and it doesn't make a lot of sense. So I don't think that we can expect those models to generalize well, right? And I think that's very important. That's also the causal bit, right? Causal and causal inference is a bit of a buzzword, of course, which is also why I put it there. But it does say, to me, this means nothing more than allows you to evaluate the outcome of all possible actions, right? So a causal model, or for me, is a model that predicts correctly the interventional distributions, right? The outcomes, the outcome probabilities for every action that I can take in any possible setting. So an MDP is a causal model, right? Always has been, always will be. MDPs are causal models, and we need such causal models in order to do planning. Why? Well, because in order to compute a plan, we need to evaluate the possible outcome of all actions in all possible states, right? We were doing these sweeps over state space, right, to do planning. We're going to use them everywhere. We're going to, really figure out what would happen if in whatever state I would do whatever action. So all of those need to be learned accurately, not only in some small part of the state space. And yeah, so getting that right, doing the right generalization, I think really requires methods that will try and learn and zoom in on the actual working of the world. And that, I think, is something we should focus on.
Anybody has thoughts on this? Causal world modeling, actively finding such models.
No, I think
Yeah, Frans said it all. Yes, Guillaume.
Well, so I'm not opposed against latent representations in principle. I just think, like, if they do not really correctly capture how the real world works, we have a mismatch, right? And in the end, the real world and that model that we've learned will not be bisimilar. The same comment I made earlier. In order for us to use an abstraction and expect it to work well in the real world, that abstraction needs to somehow resemble that real world, right? So we want it to be a form of bisimulation or epsilon bisimilarity abstraction is a formal terminology. And then we can, be confident that it will work well in the world. And then we can plan on the one model and deploy it in the real world and expect it to work well. And I just don't think that just trusting on, certainly if you just apply like a variational autoencoder with this reconstruction loss, right? Okay, so what is it being trained on? It's being trained on correctly replicating images. There's no reason that will be good in predicting the transitions or the rewards per se, if it's not trained on that, right? mu0 is trained on these ideas of value equivalence. Yeah, I only need to predict the value. I don't care about predicting next transitions or these kind of things. Yeah, same thing. It's a very weak learning signal. In principle, there's some relatively nice theory behind it, but it's a very weak learning signal. So what is this deep network really going to learn? And then, a student of mine investigated this a little bit, and yeah, so it just shows that these models that are being learned by these techniques like mu0, they're extremely overfitted, or they are overfitted to the policy that you're currently following. Well, okay, perhaps that's, sounds like, well, that's not too much of a problem. It's perhaps understandable. Yeah, we're currently following policy. We use that to learn or optimize this model. So certainly it might be better at predicting, around the current regime. But that also limits the extent to which you can use this to perform planning. right? Because yeah, you can't do your sweep through the entire state space and expect that model to perform well there. And that's precisely why techniques like mu0 need to have all these like policy priors and regularization type of things, because yeah, if you really use them to do freestyle planning, you know, what would happen if their predictions are just off. So yeah, I'm not opposed against latent representations in principle, but I think that just trusting that these latent representations magically really would capture the things that we would like is difficult. And of course, you know, then if we're talking about actually deploying these things in critical settings without any form of interpretability, yeah, I'm surprised at how far people have already gone with putting, you know, these kind of techniques actually on self-driving cars as such, right?
Have
so-
they really put them on self-driving cars, or have they really put these on self-driving cars?
Oh, I'm not certain about model-based RL, but if you look, of course, you know, like neural networks and all kinds of visual detectors, etc., they are being used, right? So yeah, and the same argument perhaps holds a little bit there. There's a lot of empirical testing, but then once in so many times there's accidents. Perhaps we're willing to accept that if the rate indeed stays very low somehow.
With high probability.
Well, yeah, but so there's no theory of that
Yeah,
though, right?
exactly.
Like,
You don't know why that accident happened, what went wrong.
yes, no question.
I have a bit more of a light-hearted question for everyone. If you would give yourself at the very start of your academic career, you're supposed to have some advice, what would you give yourself? Like, what advice would you give to yourself?
This is like one of those stock questions, the pillar, no, when nothing else is there to ask. No, I'm just joking.
That's a good.
I asked him, when I first started in Illinois, I asked Yuri Medinich, the controller, that is in your, and he responded to me, follow your heart. And I said, oh, good, I can spend my nights and then finishing my own treaty, the book. And it was, so his advice to me was the worst advice he could have given, because the miracle I got tenure. I said, oh, I'm gonna follow my heart, and my heart is not gonna get me tenure. So it's very dangerous to give an answer, there's so much luck involved, you know. Yeah, I got lucky just because, you know, if we hadn't gotten an award, I would not have tenure. I would, you know, because I was really just devoting myself to be a scholar, because that was my favorite thing, and not doing all the things you should do, and hoping that working, you know, pouring through a list. I did this, but that's good. No, okay, but I did, yeah. So it's very difficult. It really is. Everyone's different. The world changes so quickly. But you need to follow your heart to do that. How about that?
Any other piece of advice?
Thank you.
It's maybe not as well formulated in my head as it should be, but certainly inspired by not having any questions. Should we be thinking about how we formulate our rewards? And can we find a new way of formulating it? Because, you know, I was talking about we have information gain and we can have like regret as a signal, which helps us to, and when we use statistics and information, they're kind of semantic aspect, right? So we have this ambition to have general intelligence, but our reward functions are quite rigid. Then we have reward functions, for example, where you're rewarded for making a report. So then when you identify it as a new environment, and just a kind of a different take. So it's not like so mathematical, like how much fuel did we use, or how many goals did we use, or how many cookies did we consume. I don't know, being more general in the way we formulate our signals, because those are our learning signals, so that we can be more general in terms of applying the model and our learning experience outside of the environment that they're learning.
Maybe like a point in there, like the whole RL is based on this reward hypothesis, right? That you always can put a quantitative reward, how good your action or bad your action is. Now the question is whether that is true or not. That cannot be proved with RL because RL is developed on that. So people have tried to do some works last few years ago, whether reward is enough, reward is not enough, all these kind of things. I think even after all these works, this is a bit open question. Like given there's a reward, we can do RL and all other stuff we can do. And then the other point you made, using information gain and other signals, that's quite possible as I was discussing the information directed sampling and stuff people try to do. Like if you really want to just learn the structure, not to optimize anything, just become a scholar of the world, then you just gain information. Like you are not trying to maximize any other utility. So that is also fine. And in practice, if we go outside the theory and philosophy, like in practice, people do reward design. And that's a big art, like a black magic that people do to make things work in practice. But how does it work? What is a good way to design reward? Yeah. So I think that is a big open field.
I do think, perhaps adding to this a little bit, that so I like the question a lot, and I do think indeed that trying to think about perhaps more general somehow reward functions might be nice. So I know if we think of AI that is supposed to indeed complement humans, right? So or robots that interact with humans. So this is a very typical example of situation where it's difficult to specify reward functions. I mean, how much distance should the robot keep, for instance, right? These kind of then again, somehow perhaps there are relatively general reward functions, namely you ask the human once every so much time, not too often, because then you're also gonna, but whether they liked your behavior so far, and you get yes or no, right? It's a very sparse reward, but it's also very general reward. And so perhaps in terms of trying to think about general things to learn that might get us some some leeway. I'm not certain, but I do think it's a good question to potentially explore.
Also, I guess connects with now this learning from preferences or from human feedback that in reinforcement learning, that's a lot of research on it now. But I think at the end, even in these setups, when you're learning from preferences or human feedback or in inverse reinforcement learning, we still rely on that reward hypothesis because from the preferences, we're trying to discover a reward. So we're not moving away from that. And I think that that hypothesis, requires maybe, thinking. What are the limitations? And there is, indeed, the papers that discuss these limitations. That's interesting.
So I think there was reward is not enough, and then reward is enough. Yeah, and then.
Mm-hmm.
Also, so to some extent, perhaps also, I don't know. I never really particularly liked that discussion, to be fair, right? Like, I mean, it's very obvious if you define an MDP, somehow it has a reward, you can optimize it. So okay, great. If you have a competitive multi-agent setting, right, kind of like they're gonna interact in some way. You have multiple objectives. There might be a set of policies. So everything gives you something else, right? There's I don't know. I think like this is our goal. It's up to us how we want to formulate or formalize this, whether it's enough or not. I don't think that's the right question per se. Is it the most useful way to what you want to accomplish yourself? Perhaps is more important. And if we care about trying to have agents that will have quite general forms of intelligence and learning capabilities. We can argue whether that's necessary, yes or no. I would lean to yes, because I really like that as an idea. It fascinates me. If you want to make actual progress on actual real applications, perhaps it's not the best route, who knows? We'll see down the line. Right, but if that's somehow the type of research that we want to do, then we need to think about, well, how can we try and reward such more general capabilities?
Yes, so we have 5 more minutes left. One last question.
People already were like saying that maybe more advanced statistics should be introduced curriculum earlier, the same way that calculus is a core part of most of the education in pre-university. Do you think there's some topic that should be introduced or even just mentioned to students earlier?
Good question, yeah.
You know, I think that already calculus turns off people that wanting to go into technical fields. And statistics, you know, introductory statistics makes people never want to go into statistics. So we have to really think about the way we teach, you know. We really have to come up with, I mean, really do. I mean, we have to somehow teach them deep concepts without, yeah, that's the thing. And I'm still trying to figure out how to do this. This sort of linear, you know, first let's learn to add, then let's learn to multiply, then let's do calculus, then let's do differential geometry. That linear thing, it's so long that it just excludes everybody. And so yes, I agree, but only if it's done in a fun way, where you learn, you get to experiment really early on, as well as learning the deep, some concepts. Yeah. It's so boring. Introductory statistics, at least when I took it, was like the worst course on earth.
Very interesting.
Yeah.
But my colleagues suddenly, oh, this is school and it's in my own reason, just to hear about it, not even maybe do it in high school, but just hear about it.
I feel also, maybe from my perspective, now the students or the young people, I just feel like they're exposed actually to too many things, and we want them to go deep in things, not more things, but deep in things. I feel like with all these fast-paced videos and blogs, it's just too much, and we have to reduce things and focus on deep things, and then like, yeah, that's my view.
Yeah, that's so certainly I hope in case of the curriculum in my country that maybe there should be fewer subjects, but the score that you have to get much higher. So few less material that has to be mastered better. So, yeah. It's more like just about maybe just idea, not that studies, but just with it.
Yeah.
Did you have some topic in your mind yourself, or?
I mean,
And
for instance, I did bachelor in electronics, so there we had primarily linear algebra and calculus. I jumped to AI simply out of curiosity, and yeah, for me it was a big jump to suddenly catch up with the statistics. I mean, I managed to do that, but the fact that I wasn't even exposed to it during electronics, and now suddenly those topics also suddenly start to spill to other fields.
So here, I think outside AI, I will like to make a comment like, as I think again, a bit of bias of doing statistics for quite a bit, like I think basic statistical knowledge is something what we should give to everyone, because often people justify lots of things. I don't care about AI machine learning at this point, like lots of things saying this improves this by this amount of percent, GDP increased by this, volatility of market went by this, and ask most of the people what does it mean, they know nothing. They just see the number going up and down, number big and small, and you can feed them everything with that. So a basic statistical education is a necessity to be in this world of information. So I think that should be incorporated. For that, you don't have to do sufficient statistics, continued, all these things does not matter, like parametric models does not matter, but basic statistical education should be there, I think, given this age. And then the next question is, yeah, obviously going too broad is too much of a problem. People know a lot, but probably they don't know why it's happening, right? So people have lots of information now. So going in some subjects deeper, as Maryam said, is obviously much better. Like if you know little, like most of the end, like in the end you understand, you know probably a little, but you should know it clearly. You don't have to know everything in the world. There are too many people.
Yes, so it's time now. We bring the school to a close. It was wonderful having you all and the lecturers. Let's thank them. Bert is not here. He was ill, but they are here. Thank you. Thank you.